Okay, I guess while we see if anyone else shows up, how did people find the quiz?
All
All right.
the only thing I didn't like was the extinction was called E, and it kept sticking the
Oh,
number.
yeah, that could be annoying. Yeah, I think overall, like it was quite a mixed bag in terms of marks. Some people did quite well, and some people did not quite so well. So, like in some ways, as any like assessment goes, they're there to kind of differentiate. There's a certain amount to sort of say, can people do this, but also to differentiate between students. The average was about 57%, so that's a little bit low. So it probably tells me that I need to make things a little bit easier for future assessments. It might also be a little bit with the style of the quizzes, the fact that you can't go back and change your answers and stuff. So it was an experiment for me to try that like quiz format. I might adjust it going forwards. We'll see how things go on, say, the midterm. In terms of the midterm, we are still scheduled to have that in 2 weeks' time. The strike started yesterday for TSSU. If you decide not to, like that you don't want to cross picket lines or whatever, I'm not sure if there will be an actual picket on that day. Please let me know if you do not want to come to the exam for that reason, and we'll discuss possible alternatives. But I would encourage you to come to the exam if you can. Also, because it gives you an opportunity to see how you're doing and get feedback on your ability to answer these different questions. I've uploaded, or sorry, I will upload today, hopefully, a practice midterm as well. Some of the material that we've not covered yet because the midterm is not going to be until 2 weeks today. But it will give you a flavor for the kind of length and some of the sorts of questions, especially things that we've already covered. Okay, any questions?
Will that be a paper exam?
It will be a paper exam, yeah. Any other questions? Nope. Okay, today is going to be hopefully fairly nice and easy. Before we move on next week to thinking about interactions between species, we're just going to today review everything that we've done so far. It's a good opportunity to ask any outstanding questions that you might have, and go through a worked example at the end as well. Okay, so it's Friday. We'll have a nice, relatively chill day. Good. Okay, so I just want to start off by making sure that distinctions between discrete and continuous time models are clear. The vast majority of what we're going to be doing going forward will be in continuous time, but it's good to make sure that we know what the distinction is. So, okay, if we have discrete and continuous time models, when I refer to a simple population model, I'm referring to what we've done so far, just one dimension, homogeneous populations. So we can write our discrete time model in the form n sub t plus 1 is equal to some function f of nt, where f is our net growth rate. We could also write down as in terms of its net per capita growth rate. I won't do that here. And in continuous time, we would write dn dt is equal to f of n. Okay, so just notation there. And then, okay, can anyone tell me for steady states in a discrete time model, what do we need in terms of f? How do we find these?
F of n star equals c star.
Yep, so we just need to find solutions to this equation here. Any n star that satisfies f of n star equals n star. But then if we're in continuous time, what do we need to find for equilibrium in continuous time? Yeah, so here f of n star equal to 0. This is a common mistake that people often make when going back and forth between continuous and discrete time models, that they'll be doing a continuous time model and they'll try to set this dn dt equal to n star, or they'll be in discrete time and they'll be setting this equal to 0. Okay, how about stability? So if we define lambda to be our derivative, all right, df dn, in fact, I'll write it as f prime of n. F prime of n star. So let's do continuous time first in this case. What is the condition for stability? So for our equilibrium n star to be stable, what's the condition? If lambda is equal to the derivative of our net growth function evaluated at n star, what's the definition for n star to be stable? Let's do continuous time first. Yeah, just because it's slightly easier. Anyone? I probably should have put down the general solutions for these things, but I'll put them down here at the top. We have n of t is equal to n0 e to the lambda t. In this case here, for continuous time. And in discrete time, we have n of t is n0, our initial population, times lambda to the t. The reason I write those down is because if you can remember what those are, it does help with understanding stability. So for a fixed point to be stable, any perturbation we have away is going to grow at e to the lambda t. So what do we need for stability in continuous time?
Lambda less than 1.
Lambda less than, okay, so if lambda was less than 1 here, suppose lambda is a half. Think of this as this is a linear system. I should have said, sorry, these are linear. The reason I'm writing the linear ones down here is because when we do our perturbations, we linearize our system. So if we take lambda as being less than 1, but positive, then our perturbations would grow as e to the something positive times t. As t gets very, very large, that's going to go off to infinity. But if lambda is negative, then that e to the lambda t is going to tend towards 0. So for stability in continuous time, we need lambda to be negative. And positive for it to be unstable. Okay, can anyone remember the conditions in discrete time? You started to say something before about discrete time.
For greater than 1 is monotonic unstable, and between 0 to 1 is what we call stable.
Okay, yeah. So if lambda is positive, the other way of thinking of this, lambda is positive, you always get. Oh, sorry. Yeah. Getting ahead of myself there. Unstable. Thank you. So yeah, if lambda is greater than 1, monotonic unstable. If lambda is between 0 and 1, it's monotonic stable. Again, if we think about our perturbation, it's going to grow as the size of that perturbation times by lambda to the power of t. So if lambda is positive and greater than 1, then that's going to grow. If it's positive but less than 1, it's going to shrink to 0. Okay, the other way of thinking of this as well is one way of framing this is if lambda is positive, then we're always going to have monotonic dynamics. Okay. Okay, what's the other possibilities for the discrete time model?
It's between -1 and 0, it's oscillating.
Yeah. So it's oscillatory stable when we're between -1 and 0. And what's the last one? Yeah, so if lambda is less than -1, it's what?
It's unstable.
Yeah, so oscillating. So think of it as if it's positive, it's monotonic. If it's negative, it's going to be oscillating. And if the absolute value is less than 1, then we're going to be shrinking down towards 0, so it's stable. And if the absolute value is greater than 1, then it's going to be growing. I've written it again. It's because I keep thinking one step ahead of myself. Thank you for pointing it out. Oscillatory unstable. Thank you for that. Okay, and then we looked at some geometric methods. Can you remember what the name of the geometric method is for when we're in discrete time? Cobwebbing, yeah. Okay. So cobwebbing is a way of geometrically analyzing these things in discrete time without having to do too much algebraic analysis. And then in continuous time, Can you remember the name of the diagram that we drew for continuous time?
Bifurcation.
So we can do bifurcation diagrams for both of them. The method that we use to analyze stability, we would draw, say, our population n going horizontally, and then we would draw some function and then draw some arrows. Can anyone remember the name of what this was called? Begins with P. Phase line diagram. Thank you. The phase line diagram. When we go into 2D in continuous time, we're going to be talking about phase planes. So you've gone from 1 dimension to 2 dimensions, okay? But related concept, we want to sketch some functions on that phase plane diagram, and that will tell us about what's going on in 2 dimensions. So we'll draw some arrows on this as well. It gets obviously more complicated because if you're in 1 dimension, you can only go back and forth along a line, whereas you're in 2 dimensions, there are more complex dynamics that you can. Okay, so that table there hopefully is a bit of a cheat sheet when you're sort of going back and revising these things to make sure you understand the distinction between them. Okay, let's think about bifurcations and chaos. So we spent a lecture on this, and we're going to be talking about bifurcations at various points going forward as well. So you mentioned a bifurcation diagram a moment ago. That's a way of varying a parameter in our system and showing how the stability is changing, as well as also the what those equilibria or steady states actually are. Okay, so there was a question on this in the quiz, and you had to select which one it was. People generally, those is sort of 50-50 in terms of how people did roughly on that, I think. I think one of the issues people had was not recognizing how the equilibria itself was actually changing. So again, this comes down to ideas of like curve sketching. If you know that your equilibria is something like n star is equal to 1 minus 1 over something, then as that thing gets bigger, you're going to tend towards 1. Okay. So again, it comes down to some curve sketching. Okay, so we've met 3 types of bifurcations so far. Can anyone remember any of the names of any of the bifurcations? Transcritical, thank you. Can you remember what that corresponds to? Like when that occurs? Yeah, so basically when not just a trivial and carrying capacity, but you're right, when we have 2 steady states or equilibria, one stable and one unstable, and then we reach a point where their stability flips over. Okay, so we have stable, I'm going to abbreviate here, and unstable. I'll write it as equilibria or steady states, exchange, stability at some value. I'll call it mu to mu c, some critical value, where mu is just some parameter of our system. Okay, so they exchange stability. Any other bifurcations that people can remember?
Saddle.
Yep, so saddle node. Can you tell me what happens with a saddle node bifurcation?
2 equilibria will potentially collide and
Okay.
remove each other.
Yep, so a stable and unstable equilibria collide and annihilate. What was terrible at spelling an I? Each other. Okay, so that means that you kind of go from, say, 3 to 1 equilibria. Of course, this still applies in the other direction. You know, we talk about often a bifurcation parameter increasing, and you say, okay, they collide, and you go from having 3 equilibria to 1 equilibria. There's nothing special about going in that direction per se. You could flip it around. It's still a bifurcation going from 1 to 3, and they appear out of nowhere. Okay, but in one of the directions, they'll be colliding and annihilating each other. Okay, there's one more bifurcation that we've met. It was only in discrete time. Can anyone remember what this was called? Period doubling. Thank you. period doubling. So this is only in discrete time. And sort of, if this occurs at a transition from oscillatory stable to oscillatory unstable, then we end up with a cascade that eventually leads to chaos. Okay, so these are the three types of bifurcation we've met. So simple question, can simple, in other words, one-dimensional continuous time models exhibit chaos? Who thinks yes? Hands up. Who thinks no? Who doesn't want to put their hand up? That's a paradoxical one to ask, right? Okay, so they can't exhibit chaos because we don't have period doubling bifurcations in continuous time. The other thing is simply that they don't oscillate. So continuous time models in 1D, in one dimension, don't oscillate. So if we recall just from this table up here, we either have that continuous time equilibria is stable or unstable, whereas when it's in discrete time, we have this possibility of oscillations. Okay. Yes.
What do you like name them oscillate, or is that just not simple?
Yeah, that would kind of violate this simple aspect. But yeah, the reason I got a little bit of space, maybe I'll just sketch it here and erase it. We have done one of these sketches before. If we think about our population going through time, suppose we've got our logistic model in, let's do it in continuous time to start with. It increases and then eventually tends to its carrying capacity, something like this. So because we have an instantaneous rate of change, it approaches it very smoothly and it will approach it monotonically. Whereas if we are in discrete time, we make these jumps. So you start here and then say you jump to this next time point, another time point here, another time point here. At this point, our growth rate might be higher, like we might be adding too many individuals and we go above our carrying capacity. So now say you go up here and you're above your carrying capacity, which is given by this gray dashed line here. And so now we're above, so there's a net growth rate that is negative, and now we're below and positive and so on. This could tend towards it, it could tend away from it. The point is that we're overshooting, whereas in a continuous time model, we'll approach something smoothly. And that's why you get oscillations in discrete time, one-dimensional, but not in continuous time. Kind of, yes, I guess if you're going along like a railway track, it's kind of like imagine the sleepers on a railway track. They're these discrete jumps. And suppose the carrying capacity or the point you wanted to get to is between two of the sleepers. If you're in continuous time, you're going along the rails, and so you can approach that smoothly, and you don't jump to the other side. You can't jump to the other side without going through that point, right? But if you're going on the sleepers, you might step over where that point was because it's somewhere between two. Okay, so it's not a perfect analogy, but hopefully gives a bit of an idea that you're kind of jumping past a point and then have to jump back, whereas if you're on the rails, which are nice and continuous, you'll approach it smoothly. Okay, let's move on because I want to make sure we've got time for this problem at the end. So we've met two geometric methods. I say cobwebbing and phase line diagrams. Let's delete that. So what did these look like? Well, in a cobwebbing diagram, here, remember we're plotting. In both of these cases, we're thinking about our net growth function. And we can think about our net per capita growth function as well for our phase line diagrams, but I'll keep it simple here. In cobwebbing, we have our population the next time point going on the vertical axis, population the current time point in the horizontal axis. We have a diagonal. NT plus 1 is equal to NT. And then we have some growth function. Maybe it looks like this. and this is our f of nt. Okay, we need to be able to sketch that curve, and then we pick a point as our n naught, and then we just need to move vertically and horizontally between our red curve and our gray line, our diagonal. And then that will tell us, are we moving towards a point? Are we moving away from it? Are we approaching it in an oscillatory manner? Do we have chaotic dynamics? That tells us everything we need to know. And then if we have a phase line diagram in continuous time, let's just make this a little bit smaller. Phase line diagram. So we could do this in terms of our net per capita growth rate. When you do that, you just need to remember that you've factored out an n. So you might be, say, yeah, you won't represent necessarily all of the equilibria on here, but we'll do it in terms of our net growth rate here, our f of n. Here we just sketch whatever this looks like. So for example, it might look like something like this. And here, where my equilibria are. On the left-hand, sorry, in this cobwebbing diagram, our equilibria are going to be where we have an intersection between the diagonal and our growth function. When we do a phase line diagram, our equilibria are going to be when our growth function f of n is equal to 0. So this is where those equilibria are, is essentially just translating what we had in this table up here. Remember, our steady states are equilibria. In discrete time, it's when our growth function is equal to our population size. There's no change. So that means that we need to be sat on that diagonal of where nt plus 1 is equal to nt. Whereas here, f of n star is equal to 0. So we have equilibria along our horizontal axis. So that's why we see this difference of diagonal versus the horizontal axis as being where our equilibria are. Okay. So in a phase line diagram, when f of n is positive, we're going to be moving to the right. So this is a population of size n. So we can think about an initial population somewhere along this horizontal axis. And when the red curve is below the axis, we're going to move to the left. And when it's above the axis, we're going to move to the right. And that tells us the stability. So this one here is stable, this one is unstable, and this one is stable. If I had drawn this same curve as a net per capita growth rate, this curve would have been quadratic rather than cubic, and I wouldn't have had an equilibrium at 0. So there's a slight distinction here when we're doing our per capita versus our standard growth rates, but both can give you the same sort of qualitative outcome when we're thinking about our non-trivial equilibria. Okay, so quite a lot of this is all about curve sketching. We need to think about, like, how do we accurately sketch some curve? So suppose we have a curve y is equal to f of n. This is just any curve. We can forget anything about population models, but how do we accurately sketch a curve? What kind of ingredients can we think about? Okay, yeah, so we can think about the roots. So we could, for example, we don't necessarily have to do all of these as well, right? So we could find values of n where f of n is equal to 0, and that's where it's going to be crossing the horizontal axis. So just like here, you had your hand up at the back. Okay, so that tells us where we're crossing the horizontal axis. What about crossing the vertical axis? How do we find that? Yeah. So we might want to find f of n is equal to 0. We might have to find f of 0 equals what? That tells us where we're crossing the axes. We might not always want to find exactly what this is. You know, we don't necessarily need to find the roots, but say if we know that our function is quadratic, or in this case, let's take the cubic because we've got a cubic here already. If it's cubic and we've got a negative sign in front of the cubic, I know my cubic curve is going to look something like this. I might be able to deduce where these intersections are going to be. Are they going to be for values where n is always positive. Are they going to be ones where it goes through 0? Are some of these going to be to the left-hand side? Okay, so it might help you to place where your curve is. What else might we want to think about with this curve? Not to sketch it. Again, a generic curve, yeah.
We could find like with f prime, excuse me, f prime of n equals 0.
Yeah.
The maximum.
So f prime of n equal to 0 will give us maxima, minima, and also potentially inflection points. An inflection point, if you're not familiar with that, is something that would look like this. It's temporarily, not very great sketch there, but it temporarily is equal to 0, but it doesn't change direction. Again, these are not necessary in all cases, but can help you to sketch it because you might be able to help. Okay, I know that I've got a maximum here, and it's at a positive value. That would help me sketch this curve. Anything else? What about as n tends towards 0 or n tends towards infinity? And think about what happens to f of n. Okay, so n gets pretty big, got really large population size. What happens to our growth rate? Does it keep growing? Does it tend towards some constant? Does it go negative? Often we'll be finding they go negative, but not always the case. And what happens as it goes to 0? Do we approach, do we have something that is approaching at a very steep angle? Is it negative? And so on. So thinking about what happens as n varies, okay? Okay, let's go through these a little bit quicker. So what is an Allee effect? Can anyone tell me how you would describe an Allee effect to someone who's, say, not a mathematician? Yeah.
When the growth rate at like for small values of n is lower than for higher values of n.
Yeah, exactly. Yeah. So it's essentially a phenomenon where the per capita growth rate, it's important that it's the per capita growth rate here. Because if you just had your net growth rate, then kind of obvious that in most cases, a small population has a lower net growth rate than a large population. So the per capita growth rate, so per individual, it decreases as n gets small. Okay, so that's kind of like the descriptive way of saying what an Allee effect is. You could also describe it as saying that an Allee effect is where small populations may crash when they get very small or have a slower growth rate than when they're a bit larger, a slower per capita growth rate. Okay, that's just a different way of saying that. Mathematically, how do we write this down? Well, for an Allee effect, we need to have this f prime of n being greater than 0 for small n. So this capital F is our net per capita growth rate. So for small n, and this small is always essentially just close to 0. How close to 0? Well, as close as you can get to 0. Technically, if you had a very, very tiny, for n is incredibly small, 10 individuals in the population, something like that, out of a population that's normally a billion, very, very small, it could have an Allee effect. Technically, it would have an Allee effect if this is true. It doesn't matter how small that n is, okay? We also would kind of stipulate that you'd need to have f prime of n negative for large n as well, but that's sort of implied. Okay, what about a strong Allee effect versus a weak Allee effect? Can anyone remember what the distinction is between these two? How we would, looking at our per capita growth rate.
The f of n is either greater than 0 or less than 0, depending strong or weak.
Yep. Can anyone remember which way round it is? Yep.
Strong is less than 0.
Okay. Strong is less than 0, weak is greater than 0. This, again, for small n. So essentially below. The biological implications of these are then that for a strongly effect, the population can crash. So population crashes below a threshold. It's especially important when it comes to things like overfishing. I'm not included in the recap here absolutely everything we've done, so I've not included all the stuff about yield curves and things like that, but we talked about how your optimal yield, your maximum sustainable yield, could be very, very close to a critical threshold where the population collapses, right? Weakerly effects, essentially small populations recover slowly. Yes.
So that threshold would be like after that it's 0, and then once you just get entity smaller than that.
Exactly, yeah. Exactly. So the threshold is exactly that place where it changes. Yeah. Okay. I know I'm going through some of these things really fairly quickly, but obviously this is more of a recap than introducing them. And I wanted to have a bit of time at the end to discuss a worked example. Okay. So lastly, we also talked about hysteresis. Can anyone remember what hysteresis is, or a fairly simple description of hysteresis? Remember, hysteresis on our bifurcation diagram looked something like this, where we had two stable equilibria in the solid lines, and then we had a region in the middle where we've also got an unstable equilibrium between them. So it's kind of a difficult thing to describe maybe, but the main thing is that our system has memory. And by that, I mean, if say we start on this lower branch here and we move along, we'll stay on this lower branch here. So think about some value here. For a value of a parameter C, I'll zoom in so it's a little bit clearer. Value of parameter C, this is our value of n along this blue curve. But if I keep increasing, beyond some critical value, I'm now going to shoot up to some other population value. Suppose we now end up over here. But now if I decrease this parameter, and I go all the way back to where I was at this value of C, because I've started on that upper branch, I stay on that upper branch until I again come past some critical threshold, in which case I would drop back down to the lower one. So if you're in this, what's known as a bistable region, you have some memory of where you've been recently. You stay close to this branch here. Whereas if you started on this branch, you would stay close to that one. Think of this as maybe being like two valleys with a ridge between them. And you stay in the valley where you start in unless you have to cross over that ridge. And that ridge is given by this dashed line in the middle. Okay, so hysteresis is telling us something about a system that has memory. Another way of thinking of this is like different on and off thresholds. I talked about this in context of electronics. If you think of the on as sort of a different up or down thresholds, it's another way of looking at it. You've got a different threshold to go up than you do to come back down. Can anyone tell me what type of bifurcation we need to have for this to occur? There are a couple of bifurcations in that little diagram up there. Can anyone remember what ones they are? I'm going to put you on the spot because you were very hot on bifurcations earlier. Yes, saddle node bifurcations. You need two saddle node bifurcations for this to happen. Okay. This last thing here about what are the implications? Well, essentially one of the implications is that systems, once they fall into a steady state or an equilibrium, if they display this local stability and they have these different potentially quite different steady states, it can be difficult to shift from one to the other. So in the context of something like climate change, we could push systems with a warming climate, they could be pushed into a new state. And even if we then reverse that climate warming in future, a century from now, whatever, the climate starts to cool, it won't necessarily go back to where we are now because things have been pushed into another state. Again, think of it as like two valleys and a ridge. It's been pushed over the ridge and it's come back down again, but it's difficult to come back up. We have to go all the way back over that ridge again. So essentially, yes, we have these steady states that are difficult to change. So difficult to move between states. Or another way of looking at this is or reverse change. And that's reversing the change even when you take away the current thing that has precipitated that change. So if we think about something like climate change again, the temperature could be CO2 parts per million. We have a particular value somewhere, I don't know, it's around 400 parts per million or something like that at the moment, where we have a particular carrying capacity for, say, a pest species. Suppose we keep increasing that, and then it flips up to a much higher density, and then we come back in future to 400 parts per million. It doesn't necessarily mean it's going to drop back down again because it is in that other state. So it's part of the importance about thinking of, I guess, naively, we might assume if we go back to the same conditions that we have now, we would go back to the same population states that we have now, but not necessarily because they can get switched into different states. Okay, we have about 13 minutes left. What I thought I would end with today is going through a worked example. Again, this is the kind of thing you might get on an exam. So thinking about like how do we go from, say, a biological problem to constructing a model to analyzing it to interpreting what it means, what's going to happen. Okay, so here we've got a population of salmon, size N. We're seeing it grows logistically in the absence of predation. It has an intrinsic growth rate R. Has a carrying capacity K, both of these are positive. We're told that bears feed on salmon with an attack rate A, which is positive, and have a handling time H, which is also positive. And we're told exactly what the per capita predation rate is over here, A over 1 plus A H N. Okay. So we're given that information, we're asked to write down a model of the salmon population size in continuous time. We need to add a page here. There we go. Okay, so I want to write down this model. We haven't done a huge amount of model construction. This is probably something that I'll try to focus a bit more on as the course goes forwards. One way of thinking about how we construct these models is taking that word information and drawing a little schematic. Okay, so we have our population size N, and we can think about what adds to that in future and what gets taken away. So we can think about its growth rate as kind of an arrow that loops back into this population. That was net births. And we're told that this is logistic. So this is going to look like Rn times by 1 minus n over k. It's going to be our births. This is feeding back in. If it helps to think about analogies, think of it as being like a bathtub, and you've got a tap that's filling this bathtub. Okay. And then to carry that analogy over, we're also going to have some kind of removal from this. So you can think of that as the drain on your bath that's taking things out. It's going to be our predation in this case. We're told that our predation, our per capita predation is A over 1 plus AHN. So if I turn this from per capita to a total amount of predation, I need to also add in a factor of n here. Okay, so we're giving it in per capita terms. If we want to turn it into total growth rate, that's where this extra n here will come from. Okay, so sometimes it's easier to write these things down in this kind of form here before writing down an equation. So here we would have dn dt is equal to Rn times by 1 minus n over k, so that's our logistic growth, minus a n over 1 plus a h n. This is our growth function, say g of n, and this is our predation term, P of n. In fact, this P here should really be a capital P, because this was my per capita, whereas here it's a total. Okay, so that's how we could construct a model from that information we were told. Let's see what else we got. Next, we're going to be asked to use appropriate parameter substitutions to non-dimensionalize the model. Again, we've not done a lot of non-dimensionalization. Part of the reason I'm saying some of these things now is because we're going to be doing more of these things as the course goes on, but showing that we can apply, model construction and non-dimensionalization to these one-dimensional models as well. So the key thing about non-dimensionalization is we can non-dimensionalize by population density, and we can non-dimensionalize by some rate in the system, okay? So, in fact, to make things a little bit easier, so I don't have to draw capital T's, I'm going to change this to a capital T here. So what do I notice here? I notice that I have a factor of K, and that K is my carrying capacity. So I could normalize everything by its carrying capacity. So normalize the population size by its carrying capacity. I'm going to let some new variable X be equal to N over K. And the other thing is we could normalize by some rates. We have an attack rate here, A, and we have an intrinsic growth rate, R. I could normalize time by either of these. When I say normalize time or non-dimensionalized time, what I'm doing is I'm saying, rather than having some arbitrary time units here, time will be in terms of, say, 1 over the intrinsic growth rate of the population. We often do this in, say, models of infectious diseases, where you might non-dimensionalize according to the average infectious period. So time is then in terms of average infectious periods, as opposed to in something like days. You might want to do that because it gets rid of a parameter in your system and doesn't qualitatively change any of your results. Okay, so here I'm going to let little t equal R times by big T. So not everything will be immediately clear right now, but we take our derivatives of these functions. dx dn is just going to be 1 over k. And if I look at dt, d capital T, with respect to little t, 1 over r. Bear with me here if this is not entirely making sense at the moment. Hopefully it'll become a little bit clearer in a moment. Okay, why have I done that? Well, let's think about what dx dt would look like. So this would be my normalized population size in terms of its carrying capacity. So think of this as, the fraction of carrying capacity that we're at. Okay, so this will go between 0 and 1 typically. And we're going to be rescaling time according to the intrinsic growth rate of the population. The dx dt, well, what do we know? Well, we know dn, d capital T, because that's just above. To get dx dt, well, I want to get rid of this n, first of all, say. And I have something in terms of n. I have dx dn. It's not entirely correct, but the way to think about this is these dn's will cancel. Okay, so that gives me dx in terms of d capital T, but I also have a d capital T, d little t. So again, these top ones you can think of as cancelling. Okay. So this is just using the chain rule. Okay, so all we need to do now is write down what those things are. So dn, d capital T, we had above. We had r, n, 1 minus n over k, minus an over 1 plus a h n. dx dn is 1 over k, and dt dt is 1 over r. So write that as 1 over kr. Okay, what else can I do here? Well, I had a parameter substitution, x is equal to n over k. So everywhere I see an n, I can replace it with x times by k. So if I get rid of that n there, I'm going to write this as kx. This n over k here, I'm going to write as x, because we have this x is equal to n over k up here. And do the same over here with these n's. I'm going to have a kx in both of those terms. Okay. So now we can do a bit of cancelling because we have a k here in this first term, we have a k in this second term, and we have a k in this outside factor. So I've got rid of all of those k's. There's still one here, but this one here is part of several other parameters. We'll be able to deal with that in a minute. What else can we do? Well, we could write, let's get rid of, I'll do it in brown now. This r here is going to cancel with this r on the outside, as long as I also adjust this parameter here. So in fact, I'll put it on the outside. Okay, so if I bring this r into these brackets here, it's going to cancel with this r here, and there's going to be an r on the denominator here. So that looks kind of messy now, but we can write this as x times by 1 minus x minus, we had an a over r here. A and r are just numbers. So I could just define a new parameter, which I'll call b, which is equal to a over r. So b is just another number. We've got x. And then on the bottom, I would normally have r is times by 1 plus ahkx. The r has already been factored out, so we're going to have 1 plus, call it c times by x. I've defined c is equal to a times by h times by k. Okay. Like I said, we'll do some more non-dimensionalization stuff in the future. We're nearly out of time today anyway. The key thing is that if you notice now, I've got two parameters here, b and c, in this model. Whereas in my original model, I had an r, had a k, an a, and an h. So I had 4 parameters. So I had 4 parameters there. I've got 2 parameters here. These models are mathematically equivalent. All I've done is I've rescaled time. I've rescaled the population sizes. All the equilibria, all the stability, all of that won't change. It's just like translating between these two things. But now I don't have to think about 4 parameters. I only need to think about 2 parameters. Everything gets collapsed down and it makes the problem a lot simpler. So we do this non-dimensionalization quite a lot. Like I said, we will come back and we will do more of this in future. Okay, the last thing, see if I've got just about enough time to do these sketches. So we want to sketch a couple of curves here in terms of their, so we asked to use sketches to determine the qualitative dynamics of this model, assuming that there is always at least one non-trivial equilibrium, and consider 2 different scenarios. A is less than r or A is greater than r. So A is less than r corresponds to the case, let's do it 2 cases here, side by side. A is less than r and A is greater than r. What does that actually mean? Let's do A is less than r here. Well, that just means that B is less than 1. And on this right-hand side, if we have A greater than r, then B is going to be greater than 1. Okay. So just like when we did our phase line diagrams before, we can split this function into a growth function and a predation term. And when the growth function is greater than the predation function, our population is going to grow, and otherwise it's going to shrink. So let's draw our per capita growth function in this scenario here. it's just going to be 1 minus x. We've got 1 here. That's our per capita growth function. And we're told that our predation term, we have b less than 1. So that means that we're going to intersect down here. And so we have 1 intersection. And on this right-hand side, and b is greater than 1, we'll have 2 intersections. Okay, we're kind of run out of a bit of time today, so I'm going to stop there. I'll upload the rest of the solutions. It might be worth working through this one again in your own time. But the key thing I want you to take away from this is that we can construct a model based on some biological description. We can then simplify that model by non-dimensionalization, and we'll be talking more about non-dimensionalization in the context of species interactions, but we can do exactly the same in 1 dimension. And then we can, just like we've done with our phase line diagrams before, we can draw some sketches. This here, I've had to rush through a little bit. I will upload the solutions to that, though, so you can step through them. And if you have any questions about that, you can ask me through at the office hours. Okay. Yes.
Why is the default curve unstable?
Sorry, why is the
For a recurrent the curve, the default curve is still.
sorry, did you mean this that should have been a B? Sorry. Yeah, I think the little curve on the B didn't work. So these were per capita curves in both of these cases. So per capita curves in both of these cases. This was a 1 minus x, our growth function, and this curve here was a b over 1 plus cx. B over 1 plus cx. So when x is equal to 0, on this curve here, our predation curve, we have our predation is equal to b. If b is less than 1, then we only have 1 intersection. On this one over here, if b is greater than 1, we have 2 intersections. And so just like before, when our growth curve, when our green one is above the red one, we'll move to the right. Vice versa, we'll move to the left. So in this case, we just have 1 stable non-trivial equilibrium. Here, we have an unstable non-trivial equilibrium as well as a stable non-trivial equilibrium. This one over here is actually describing an Ali effect, where this one would go to 0. Okay, I'm conscious that we've gone over by a few minutes. Apologies for that. We spent a bit longer on the review than I was expecting. That's fine. I have office hours now in case anyone wants to continue going through this. If not, have a good weekend, and I will see you next Wednesday. No class on Monday, remember. Okay.